Chemical Equilibrium Part 7, the reaction quotient Q for non-equilibrium systems. Okay, so up till now we've been discussing systems at equilibrium. And now we're going to start adding in what happens when we have non-equilibrium conditions. The central concept in all of this is that a chemical reaction system is either at equilibrium already or it's on its way to equilibrium. So we want to figure out how to determine if a reaction is at equilibrium or not. And the way that we do that is with something called reaction quotient Q. And so we can calculate the value for the reaction quotient and we'll compare it to the value of the equilibrium constant K. And if those two values are equal, then the reaction is going to be at equilibrium already. So the big question is, how do we calculate Q? And it turns out that that's actually really easy. And the reason why it's easy is that we're going to use the same equation as the equilibrium constant expression. So this expression right here, the only difference between what we've been doing for the equilibrium constant expression and Q is that we're going to change, instead of K, we're going to have Q. But we use the same setup, so products over reactants, each product and reactant raised to its coefficient power. So the expressions are exactly the same. Now, we only use the equilibrium constant expression at equilibrium, but Q can be calculated anytime, so under any conditions. So this is just a summary of that idea. So we can calculate Q anytime we want, and we're going to compare that value to the value for K, which is under equilibrium conditions only. So how do we compare those two values? So we're going to compare the value for Q that we calculate at some time with the value of the equilibrium constant. And then we can use that information to figure out which way the system will shift, or the reaction will shift to go to equilibrium if it's not there already. Now, if Q is smaller than the equilibrium constant value, so in other words, Q is less than K, then the reaction is going to shift toward products. That's basically reacting in the forward direction. Let's just talk about that a little bit more. So if Q is less than K, and remember, it's products over reactants, then that means there are either too many reactants, this number is too large, so that's going to make this number smaller than K, or this number is too small. Either way, you can think about it. So you can either think about not enough products or too many reactants. But both of those ways of rationalizing it will help you figure out which way the reaction is going to go when Q is less than K. So I like to write out this expression for myself to remind myself, products over reactants. Now, what happens if Q is greater than K? So that means Q is larger than K, and we can rationalize this as having too many products. So if Q is larger than K, then we have more products than we would have at equilibrium, or too few reactants. You can think about it either way. And so the reaction is going to shift to use up products or create reactants. So either way, it's going in the reverse direction. Now, what happens if Q is equal to K? Now, this is a happy situation because basically it just means that the chemical reaction is already at equilibrium. So when Q is equal to K, the system is at equilibrium already. Okay, so let's do an example problem. So we have our reaction where we have nitrogen dioxide dimerizing and forming dinitrogen tetroxide. And we know our equilibrium constant. Okay, so K is equal to 0.125. Now, we are given some reaction conditions. So we have 1 atmosphere of nitrogen dioxide and 0.75 atmospheres of dinitrogen tetroxide. Now, we want to figure out whether this reaction is at equilibrium or not. And then we're going to justify our answer. So what do? Well, the first thing we're going to do is calculate Q. So we have 1 atmosphere of nitrogen dioxide. So we're going to plug that into our Q expression, which remember is just the same thing as the equilibrium constant expression, except we can calculate Q at any time. So we're going to put in 1 atmosphere to the second power because of this coefficient. And then we're going to plug in 0.75 for our products, dinitrogen tetroxide. And after we calculate that, we're going to get 0.75. So K is 0.125 and Q is 0.75. So Q is larger than the equilibrium constant value. And so thinking about products over reactants, this means that this system has too many products. It has more products than it would have at equilibrium. So that means the reaction is going to shift toward reactants. It's going to go in reverse. So it's going to use up dinitrogen tetroxide to make more nitrogen dioxide in order to get to equilibrium. Okay, so next we're going to talk about Le Chatelier's principle, and that's 3 parts. We're going to talk about concentration, pressure volume changes, and temperature.